Open, make sure you get there. Once you do, take like 2 or 3 minutes and work through these bell work problems.
Oh, did I put the wrong document up?
We gotta figure that.
Oh, we're good?
Yeah.
Okay, sorry about that.
No, you're good. It was probably on my end, so. What's that?
I don't know. I should have did that third and fourth.
Remember, inverse sine, we're looking at quadrants 1 and 4. Inverse cosine, we're looking at quadrants 1 and 2. Yep, your answers are always going to be in radians.
In this chapter, I really research
But it's all trig, like a calculator will just give you the answer. So. Yeah, no calculator this chapter. We'll help you out a lot, though. We'll give you that blank unit circle.
Wow, thanks.
We were feeling generous.
What would I do without that?
No, seriously,
Give me on your fingers how many of the 5 you feel like you got down on your paper and you're confident in your answer.
I haven't wrote down on my paper yet.
Okay. Well, let's get going then. If you're not 100% sure, just put down your best guess. Alexis, which one? Which one are you working on right now?
7 over 2.
Yeah, we'll talk about it. You should be confused.
-2.
Yeah, good. Raise your hand if inverse sine of 7 over 2 or inverse cosine of -2, those two are confusing you a little bit. All right, yeah, good. We'll talk about it. Make sure those other 3, you have an answer down for those. Those other 3 we covered yesterday. Hopefully you're feeling confident about them. All right, so now we're going to start going over them together. Inverse sine, is sine our x-coordinate or our y-coordinate? Y-coordinate. And inverse sine is which 2 quadrants? 1 and what?
1 and 4.
1 and 4. Yep. So we know by extension that our possible answers could be something between -pi over 2 and pi over 2.
Yeah.
Our answer is going to be somewhere in that range. So inverse sine, we got to look over at our unit circle. We said we were going to look at quadrants 1 and 4. What was it? Negative root 3 over 2? Was that it? Was that the question? I'll look back. Yep. So we're looking for the y-coordinate on the right-hand side of our graph, or of our unit circle. We're looking for our y-coordinate that matches with our input, that matches with negative root 3 over 2. It's going to be down at this point at 5 pi over 3. Is 5 pi over 3 an acceptable answer? Nope. For the inverses, when we evaluate, the reason we have to make it negative, so we said this was our point, is for the inverses, we take the shortest route to that point. The shortest route is to just go back by negative pi over 3. The long way around, which is what we've been used to all through chapter 6, gets us to the same point, but it's not within that restricted domain that we talked about yesterday. So it doesn't work for the inverse. So our answer, negative pi over 3. Now looking at cosine, what's our coordinate for cosine? X or Y? X, yep. And which quadrant do we look at for inverse cosine? Which quadrants? Yep, 1 and 2. It's either going to be in quadrant 1 or quadrant 2. The x coordinate we're looking to match up on our unit circle is negative 1/2. Looking at our unit circle, that's going to happen right at this point here. We don't have to worry for the inverse trig functions that are restricted to just quadrant 1 and 2. We don't have to worry about switching around our radians. Whatever we see, we're good with. So our answer right here would just be 2 pi over 3. Yep. Why do we what? Move it? Remove it. We removed it because for our inverse sine and inverse tangent, we need our answer to be between negative pi over 2 and positive pi over 2. 5 pi over 3 is outside of that bounds. So it can't be one of our possible answers. So we had to figure out a coterminal angle that is between our bounds. That coterminal angle, we subtract 2 pi from 5 pi over 3 is one way to think about it. And that gives us negative pi over 3. Just know whenever we're working in quadrant 4 with an inverse, we're going to be counting negative. We're going to be counting backwards. So we didn't go around counterclockwise, 5 pi over 3. We just went around clockwise by pi over 3. When we're moving clockwise, it's negative. So then it's negative pi over 3. Remember, these radians in quadrant 4 are going to just be the negative reflections of whatever was up in quadrant 1. So if you're like, wait, what's the negative of 5 pi over 3? Just look up. It's right below positive pi over 3. So that means that's going to be negative pi over 3. Looking at this next one, inverse sine of 7 over 2. Inverse sine, it's our y-coordinate. Like we already said, we're going to be looking at quadrants 1 and 4. So we need to find a y-coordinate in quadrant 1 or quadrant 4 that's equal to 7 over 2. What's the radius of our unit circle? Anybody? Radius. What? Pi? Not quite. That's the circumference, or half the circumference. 1, yes. Our unit circle from the origin to any point, aka its radius, is 1. Is 7 halves greater than or less than 1? Greater than 1. So our sine coordinate is going to be that y coordinate. If you notice, none of these coordinates on our unit circle, if you just look at an individual coordinate, none of them are greater than 1. They're all between negative 1 and positive 1. So we were asked to find where our y coordinate is 7 over 2, or 7 halves. Since 7 halves is greater than 1, it's not possible to find on our unit circle. Does not exist. That's something you didn't see yesterday, so it should have kind of been a little bit confusing. Wanted you to think about it before I just showed you. If the coordinate for cosine or sine, if you can't find that coordinate on your unit circle, it's not good. Maybe you got to look a little bit harder. But if you look, double check, triple check, and it's still not there, that's probably because it's a value that does not exist. Another way to verify, if it's further away from 0 than 1, so 7/2 is greater than 1, then it can't be a coordinate on our unit circle, so it's just going to not exist. Inverse sine of 1. So we got to figure out in quadrants 1 or 4 when our y-coordinate is 1. That happens right up here at the top. So our answer for that one is just pi over 2 radians. Anyone have an idea now for inverse cosine of -2? Does not exist. Yep. Undefined, does not exist. And so it works the same way with the negatives. You can't have a coordinate past -1. You can't have a coordinate past +1. They all have to be equal to 1 or -1 or between, within that range. -2 is outside of that range, so it's not a possible input. So if we try to input it, we're just going to get does not exist. It's like on your calculator when you type in like a negative number under a square root, and it's like a syntax error. It's kind of like a syntax error for trig. Any questions with our bell work problems? All right. So now inverse tangent. Inverse tangent, we got it down as the last thing we wrote down yesterday. What were the two quadrants we restricted tangent to? Quadrant 1 and quadrant 4. Remember, when we're restricting our domain for an inverse trig function, we always include quadrant 1. We always include from 0 to pi over 2. Now from there, we have to see which one's going to be 1-to-1 or pass our vertical and horizontal line tests. Tangent's a little bit funny because both the positive and negative 90 degrees, right? Both if we looked at that quadrant, the positive, so the second quadrant or the fourth quadrant, it would pass our vertical and horizontal line tests. So now we kind of have to look at a tiebreaker. And that tiebreaker, clear ink, that tiebreaker is, will either quadrant allow us to be continuous? Here, if we go back and use quadrant 4, we're going to have a continuous line. If I was drawing that tangent function, I wouldn't have to even pick up my pencil. But if I did quadrant 1 and quadrant 2, and I was drawing it, I'd have to pick up my pencil. I would lose what we call continuity. And so we kind of have two good choices, two possible domains that would have been 1-to-1. We have to pick one of them, and we picked the one that was continuous. So make sure, if you didn't write it down yesterday, inverse tan is going to be quadrant 1 and 4. And our domain restriction, our possible answers, is going to be from -pi over 2 to +pi over 2. Remember, that's a soft bracket around -pi over 2 because at both of those edge brackets, we see at both -pi over 2 and +pi over 2, we have an asymptote. When we have that vertical asymptote, we're going to be undefined. We see it on our unit circle by a straight up and down kind of line from the origin through the point. Remember, the key to 1-to-1 was both that every input has one output and every output has one input. So in chapter 7, it's not allowed. We cannot have two answers for one question. So that's why this is a soft bracket. It's the way we make sure, if we were asked, what's inverse tangent of undefined? We would only have one answer. And that answer would just be +pi over 2. Yeah, so it's like a little bit confusing because remember our inverse trig functions, an inverse function in general is going to change which one's your input and your output. So looking at this, when we're restricting which x values we look at, we're restricting the domain. But then when we take the inverse, we're restricting the domain of the parent function. But then that becomes the range or the answer of our inverse function. So that's why when we restrict the domain of our parent function, we are giving ourselves our possible answers for our inverse function. Does that make sense? Great. So now, before we do these examples, I want to look at this. So that's our tangent. That's quadrant 1 and quadrant 4. That's the half of the unit circle that we look for when we're evaluating tangent. Tangent is what over what? Sine over cosine. What about coordinates? Yep, y over x. One way we can think about tangent is we can think about tangent as the slope of the line connecting our point with the origin. And the reason we're allowed to think about tangent like that is because the slope formula that you probably learned back in Algebra 2 was y2 minus y1 over x2 minus x1. Well, our x1 and y1, that point, is going to be the point at our origin. And what are the coordinates of our origin? 0, 0. So y1 and x1 are just 0. If we cross that out, we see that the coordinates of our point are going to give us the slope of the line connecting the origin and that point. And if you think about tangent as the slope of that line, it gets a little bit easier to remember what tangent's going to be at specific angle measures, which you kind of could get by chapter 6, just keep, change, flipping. But think about it, for chapter 7, now we're going to give you a tangent value or give you a slope, and you have to tell us the angle measure. Well, that's going to be a little bit difficult because you would have to work backwards through your keep, change, flip, and that might involve some guess and check, a lot of work. No one wants to have to keep, change, flip multiple times just to solve one problem. But here's how we can kind of work around it. What's the slope of a vertical line? Anybody? Why don't you think about it? Can a vertical line have a slope? No. Think about it. Our slope equation relies on a difference in x's. A vertical line only happens at one x. That puts a 0 in our denominator. What happens when there's a 0 in our denominator? DNE, undefined, right? So, long story short, tangent of pi over 2, tangent at that point right there, is going to be undefined. And you could have told me that by saying, yeah, it's the y over the x, 1 over 0, that's undefined. But you could have also told me that by looking at the slope of the line connecting the origin to the point on the unit circle. The slope of the line, well, it was vertical. A vertical line has an undefined slope. What's the slope of a horizontal line? What'd you say? 0. Yeah, 100%. Remember, slope, one way to kind of think about it is a positive slope leans back. It's all about kind of that tilt. A negative slope leans down. It's kind of like negative slope's like a slide. Positive slope, maybe like a staircase, right? You're going up or you're going down. If you're not going up or down, we say that slope is 0. Tangent of 0 equals 0, which is what we already knew. The reason this is important is because, remember, our inputs and outputs in this chapter are getting flipped on us. So instead of getting a point to know, okay, I got to compute the y over the x, you're given that y over the x, or that slope. So a question that you might be asked this chapter is, what's the inverse tangent of undefined? And what would we say? Any ideas? Pi over 2, yes. 100%. Good job, Chris. Pi over 2. The way we can think about this, and the way that it seems like we're giving ourselves more work, but I promise we're not, is when you see inverse tangent, what we're giving to you is the slope. What you need to give to us is the point, the angle measure that makes that slope possible. The only angle measure in our restricted domain that makes undefined possible, or a vertical line possible, is that point pi over 2. So then if I ask you what's the inverse tangent of 0, you could read that as, what angle is going to give me a slope of 0, or a horizontal line? 0, yep. 0. Which point do you think is going to give us a slope of 1? AKA the answer to inverse tangent of 1. Negative pi over 2? So negative pi over 2 would be down there. The slope of that line would be vertical. Which lines have positive slopes? Those 3 lines or those 3 lines? Quadrant 1 or quadrant 4? Quadrant 1. Pi over 4. Yep. Pi over 4 is going to give us a slope of 1. The line that cuts our quadrant in half is gaining width and height just as fast. It's going to give us that 45-degree angle. Pi over 4, it's going to have a slope of 1. If you can remember that pi over 4 has a slope of 1, then you pretty much know all the rest of your tangent values, just from what we've already put up. Because if you look at it, that blue line or that horizontal line, slope is 0. That green line, slope of 1. And that red line, is an undefined slope. So now that kind of leaves us 2 values, pi over 3 and pi over 6. If you're on your phone, I'd like you to make sure you're locking in for this. It's going to be kind of really confusing if you're asked one of these and you don't have a strategy. It's going to take a lot more work. So, first off, tangent at pi over 3, just normal tangent. We would say, okay, it's y over x, or root 3 over 2 over 1 over 2. If you trust me, if we keep change flip that, those 2's would end up canceling, and we would just get root 3. So tangent of pi over 3 is root 3. Now let's think about that like slope. What's the bigger number, root 3 or 1? Just off the top of your head. Raise your hand if you think root 3 is bigger than 1. Couple. Raise your hand if you think 1 is bigger than root 3. Couple, about 50-50. Good. Before I answer that question, I'm going to ask you another question. What's bigger, root 1 or 1? Same. Yep. Remember, the square root of 1 equals 1. What's bigger, the square root of 3 or the square root of 1?
Square root of 1.
Square root of 3, yeah. They're both the same function, and 3 is larger than 1. So we know the square root of 3 is bigger than the square root of 1. So if we go back up, we know the square root of 3 is bigger than the square root of 1. Square root of 1 is just 1. So square root of 3 is bigger than 1. That's going to be huge for us. Because what we can get asked is, What's the inverse tangent of square root of 3? And it's going to be hard to just y over x work our way backwards through that. But here's how we can approach this a little bit quicker. If we approach this as, okay, inverse tangent, that's slope. So now looking at it, and I'm looking at quadrants 1 and 4. So in quadrants 1 and 4, I have to find the point that has the slope of root 3. The next thing I think is, okay, is root 3 positive or negative? Positive, yep. So it's going to be bigger than 0. Root 3 is bigger than 0. Look back at our unit circle. So these were all our possible tangent values. We know root 3 is larger than 0, so that's going to put us in quadrant 1. From there, we asked ourselves, is root 3 bigger or less than 1? Bigger. We just answered that. We know root 3 is larger than 1 because we know root 3 is larger than root 1. So now let's look back at our quadrant. Which slope represented, which radian represented a slope of 1? Pi over 4. Yep, the point that cuts our quadrant in half. We know that the slope of the point we're looking for is steeper or bigger than pi over 4. That leaves two options, pi over 3 and pi over 2. What's the slope of pi over 2? We already talked about it. Undefined. So we've sandwiched. We know that this slice right here is going to give us the slope of the point we're looking for. So we didn't even have to do any real computing. We just used our number sense, and we can figure out that the inverse tangent of root 3 is just pi over 3. Question?
So is it only with cosine and sine that if it's over 1 that it's, I mean.
Yes. Yep. Because think about our possible tangent values, our possible slopes, go all the way from undefined to undefined. And it's every number in between. So there's a point, if I asked you like pi over 2 minus 0.00001, so like just to the right of pi over 2, that slope, that tangent would be super big. So that would be, and it goes all the way up until it takes to undefined. And so yeah, every possible answer is possible for tangent. You can't just rule out if it's bigger than 1. So now, last but not least for tangent, the last thing that you could see is what's the inverse tangent of root 3 over 3. And we're going to kind of apply our same exact philosophy. Is root 3 over 3 positive or negative? Positive. So it's going to be larger than 0. Is root 3 over 3 bigger than 1 or less than 1? What's it take for a fraction to be bigger than 1? Does the numerator have to be larger or the denominator? Numerator. What's bigger here, the numerator or the denominator? So is it larger than 1 or less than 1? Less than 1. So we know that the slope of this slope is going to be tied to a point that is a slope greater than 0 and less than 1. What's our only option? Pi over 6. We said it has to be less than the point that gave us slope of 1 and greater than the point that gave us the slope of 0. The only radian or angle measure that works is right there, pi over 6. If we were given a negative inverse tangent, we would follow the same kind of process, except we would be working in our negative quadrant. For example, if we got inverse tangent of negative root 3, first thing we would think to ourselves is negative root 3 greater than 0 or less than 0? Yep, so we're going to be in quadrant 4. We're going to be somewhere with a negative slope. First things first, what do we think the slope is of negative pi over 4? Negative 1, yes, negative 1. The points are the same except there's just one negative. Is negative root 3 just by itself? Is that going to be large? Is that going to be between negative 1 and 0 or between negative 1 and infinity? Yeah, exactly. It's going to be further away from 0 than negative 1. So it's going to be steeper, and this time in the negative, than negative 1. That only leaves us one option. That point right there. Remember 5 pi over 3, we think about that as negative pi over 3. So then our answer for that question will just be negative pi over 3. One thing that's nice about the inverse tangents is that there's only so many options. So eventually you can kind of start recognizing it and trying it. I want you real quick, we just went over all 4 of these. So they should already be in your notebook. Attempt these 4 problems. If you really want to challenge yourself, try to not look at your notes and just kind of use the process we were discussing. Can you give those problems a try, please? The biggest thing to remember for inverse tangent is we're not given a coordinate, we're given the slope. You just got to find in quadrants 1 and 4 where that slope's going to match up. Which radian gives us a slope of 1? Pi over 4. Which 2 points give us an undefined slope, or that vertical line? Pi over 2 and negative pi over 2. Which one do we pick? Which one is actually included in our domain restriction for tangent, inverse tangent? Pi over 2, yep. Inverse tangent and sine are nice because when it's a negative, it's just going to be the negative reflection of the positive. So inverse tangent of negative 1 is just going to be negative pi over 4. Can you go up to the board and show me it?
Which one? One right there. Or for this? It was pi over 6, right?
Yeah, I wouldn't have you write down if he was wrong. Do we agree with Chris's answer on arctan of root 3 over 3? No? What do you think it is? Oh, okay, okay. That's more personal. Great, so Chris, how'd you know it was pi over 6? Walk me through. Did you just look at your notes and you remembered from what we just wrote down? Or did you follow our process?
Yes, but the process, because pi over 4 would just be 1.
Yep.
But root 3 over 3 is less than 1, so I went
Yeah.
to the one that's right below.
The only option left. Good. That's if your brain thinks like that, that process will not let you down. It will not let you down. Well, great. So last thing we're going to do today is we're going to look at something we like to call composite functions. Who remembers something in algebra at some point that you guys called like f of g? Yeah. So f of g is, you might not remember the name for it, that's a composite function.
Oh, yeah. We did the F and the little 0, not 0, up.
Yeah.
That.
It looked like it spelled out fall.
Yeah.
That's how I was.
Did that last week.
Okay.
Yeah.
Good. Okay. I wasn't even remember.
Oh, yeah.
So composite functions, the way we solve composite functions, well, first thing, the way they're made, is it's going to be a function inside of a function. The way that we solve it is the inside part, or the part that's inside the parentheses, we solve first. The answer for that inside part, we just plug in or substitute into the outside.
What?
Kind of, yeah. Do what's inside the parentheses, and then you just evaluate the whole thing. It's easier to see than here. So here, inverse cosine of pi over 2. Thank you for letting me know. First thing I do is I'm going to pull out what's inside the parentheses. Cosine of pi over 2. Is this an inverse trig or a normal trig question? Yep, you're given an angle, and we're asking you for a coordinate. Are we asking you for the x or the y? The x, because it's cosine. So you got to figure out what the x is at pi over 2. Find pi over 2. Yep, it's going to be 0. So then you rewrite this as inverse cosine of 0. And now that's something that you've learned to solve over the past day and a half, hopefully. Inverse cosine, we look at which quadrants? No, 1 and 2. Cosine is 1 and 2. Sine and tangent is 1 and 4. So you look at quadrants 1 and 2, and you have to figure out where that x coordinate is 0. It's going to be at that point right there, pi over 2. And that's your final answer. On a test, when we ask you to evaluate a composite function, please show both steps. Show yourself solving the inside and then plugging the inside back to the outside. That kind of just helps make sure you're going to get some points. If you messed up something at the end, but you only wrote down the final answer, it's really hard to give you partial credit. If you show us both steps, the way I did here, let's say for some reason you thought inverse cosine of 0 was pi over 4. Well, since you got there, I'm still giving you half your points. Show your steps. Looking at inverse sine of 5 pi over 4, the first thing we're going to do is we're going to evaluate sine of 5 pi over 4. Remember, normal trig function. First time we've been in quadrant 3 since chapter 6. 5 pi over 4, we're looking at the x coordinate. It's going to be negative root 2 over 2. So the way we rewrite that is it's going to be inverse sine of negative root 2 over 2. Remember, there's no quadrant restriction for the normal trig functions, only for the inverse trig functions. Now we look at inverse sine of negative root 2 over 2. Inverse sine, we're restricted to quadrants 1 and quadrants 4. We got to figure out where that y coordinate is going to be equal to negative root 2 over 2. That's going to happen down here at 7 pi over 4. 7 pi over 4 is negative pi over 4. Yep. However you need to remember it, just make sure we write quadrant 4 for an inverse problem as 0 to negative pi over 2.
So quadrant 3 isn't used?
Quadrant 3 doesn't get used for the inverse, but it can when we're going forward. Like we use quadrant 3 for sine of 5 pi over 4. So if you're kind of looking and you're like, okay, I know an inverse undoes the normal function, you're kind of right-ish. You're like 95% of the way there. But if you were then to go say, well, these two are just going to undo each other, I know my answer is going to be pi over 2, you would only be right about half the time. Do not trust that trick. If we were to use that trick down here and say, okay, inverse sine of 5 pi over 4, these are the same function and one of them's an inverse and they'll undo each other, we would have said our answer was 5 pi over 4. It's not. Negative pi over 4 isn't even a coterminal angle for 5 pi over 4. 5 pi over 4 is in our third quadrant. Negative pi over 4 is in our fourth quadrant. You aren't even close to right. Trust the process. Evaluate the inside, plug the inside, and evaluate the outside. The last thing you guys are going to do today is just this last problem. Try it by yourself. Good job. Inverse cosine of that. Close. I disagree though. You need to figure out quadrants 1 and 2, right? You need to figure out where it's root 3 over 2. If you evaluate the inside, you're going to get that inverse cosine. The inside cosine of 11 pi over 6 puts us right here. I know it's hard to see, but that x-coordinate is going to be root 3 over 2. Then to take it home, we just need to apply our inverse rules that we've learned. Inverse of cosine of root 3 over 2. Root 3 over 2 is going to be in quadrant 1 or 2 right there. So then our final answer is just pi over 6. Remember, inverse cosine, we're given the x-coordinate, and we need to figure out the angle measure. And our angle for inverse cosine is going to be in quadrant 1 or quadrant 2. Any general questions with what we learned today? All right, before you get your math journals put away, I'm going to hand out glue sticks and a handout that we're going to do tomorrow in class.